Section 8.6 Alternating Series. In this section, we turn our attention from non-negative term series to series with both positive and negative terms. There are two classes of series for which the successive terms alternate sign, and each of these series is called an alternating series. The first class involves series of the form sigma minus 1 to the power of k multiplied by ak. The second class involves series of the form sigma minus 1 to the power of k plus 1 multiplied by ak. In both cases, ak are positive. We consider an alternating series sigma k from 1 to infinity minus 1 to the power of k plus 1 multiplied by 1 divided by k, which equals 1 minus 1 half plus 1 third minus 1 fourth plus 1 fifth minus 1 sixth, etc. We investigate the conversions of this series by examining the sequence of partial sum. The first sum is 1. We plot this value on a number line. The second sum is 0.5. We plot this value on the same number line. The third sum is 0.8333. This is a little less than 1. The fourth sum is 0.58333. This is a little greater than 0.5. The fifth sum is 0.78333. It is a little less than 0.8333. The sixth sum is 0.61666. This is a little greater than 0.8333, etc. We have seen that the terms of this sequence comes closer to each other as n grows large, and they seem to approach a limit. The general term of this sequence is ak equals minus 1 to the power of k plus 1 multiplied by 1 divided by k, which tends to 0 as k tends to infinity. In general, the fact lim ak when k tends to infinity equals 0 tells us very little about the convergence property of the series sigma ak. However, an alternating series must converge if the absolute value of its terms decreases monotonically towards 0. This result may be stated as follows. Alternating series test. An alternating series sigma minus 1 to the power of k multiplied by ak, where ak are positive, and both of the following two conditions are satisfied. ak is a decreasing sequence, and lim ak when k tends to infinity equals 0. Then the series must converge. When you test the alternating series for convergence, it is wise to begin by computing the limit lim ak when k tends to infinity. If this limit is not 0, you know immediately that the series diverges by the divergence test. However, if this limit is 0, you can show that the alternating series converges by verifying that ak is a decreasing sequence. We consider an example. Test the following series for convergence. Sigma minus 1 to the power of k multiplied by 1 divided by k. This series is called the alternating harmonic series. The series can be expressed as sigma minus 1 to the power of k multiplied by ak, where ak equals 1 divided by k. We have lim of ak when k tends to infinity equals 0, and the sequence ak is decreasing. Thus, the alternating series test tells us that a given series must converge. The second series is sigma minus 1 to the power of k multiplied by 3k divided by 4k minus 1. This series can be expressed as sigma minus 1 to the power of k multiplied by ak, where ak equals 3k divided by 4k minus 1. We have lim of ak when k tends to infinity equals 3/4. Thus, the divergence test tells us that the given series must diverge. The first series is sigma minus 1 to the power of k multiplied by k squared divided by k cubed plus 4. The series can be expressed as sigma minus 1 to the power of k multiplied by ak, where ak equals k squared divided by k cubed plus 4. We have lim ak when k tends to infinity equals 0, and the sequence ak is decreasing. We can verify this by computing the derivative of ak and show that it is negative. Thus, the alternating series test tells us that the given series must converge. If sigma ak converge, then sigma absolute value of ak may either converge or diverge. The two cases that can occur are given special names. The series sigma ak converge absolutely if the related series sigma absolute value of ak converge. If the series sigma ak converge but not absolutely, which means that the related series sigma absolute value of ak diverge, then it converges conditionally. We take an example. The series sigma minus 1 to the power of k multiplied by 1 divided by k squared is an alternating p series with p equals 2. The related series sigma 1 divided by k squared converges synthesis of p series with p equals 2. Thus, the given series converge absolutely. The series sigma minus 1 to the power of k multiplied by 1 divided by k is an alternating p series with p equals 1. The related series sigma 1 divided by k diverges since this is a p series with p equals 1. The given series sigma minus 1 to the power of k multiplied by 1 divided by k converges by the alternating series test since the sequence 1 divided by k tends to 0 and is decreasing. Thus, the given series converges conditionally. We consider another example. Test the series sigma cosine k divided by k squared for absolute conversions. We consider the related series sigma absolute value of cosine k divided by k squared. Since absolute value of cosine k divided by k squared is always less than or equals to 1 divided by k squared, and the series sigma 1 divided by k squared converge, so the series sigma absolute value of cosine k divided by k squared converge by direct comparison test. Thus, the given series converge absolutely. The following is a statement of the generalized ratio test. The ratio test for positive term series can be generalized to apply to arbitrary series. To do this, you have to check the limit lim when k tends to infinity of the absolute value of ak plus 1 divided by ak. If this limit is less than 1, then the series sigma ak converge absolutely. If this limit is greater than 1, then the series sigma ak diverge. This is the end of section 8.6. Thanks for watching.